Let's consider a problem situation dealing with forces in circular motion. So we have the track event of shot put. Iron ball moved in a curved path through the throwing motion. Ryan Krauser set an Olympic record throw of 22.52 meters in 2016. So we have a delta x that the ball travels in linear motion. Now, in the throw, well, we've got the ball that has a mass of 7.3 kilograms. Now, focusing in on the throwing motion. In the throw of the shot put, the ball is moved in a curved path of radius 55 centimeters. So we know we have a curved path. So this is different than the linear throw. This is actually in the throwing motion. The radius 55 centimeters, and then released following a forward extension of the arm. At the end of the curved path, the shot put is traveling 4.2 meters per second. Okay, so if you can imagine, in my wonderful artwork here, we're not even going to try to attach the arm here to the ball. Here's the ball. Imagine the arm goes up there. So in the throwing motion, the person is going to twirl around and the ball is going to go in a curved path. That has the radius of 55 centimeters. Following that, then the arm extends forward to give that final thrust, that final push. And then the ball goes flying, and the ball flies 22.52 meters. So in this, what we're looking for in part A is the centripetal acceleration, and then B, the centripetal force. So in this whole motion, we are focusing around this part of the motion right there. Not the arm moving forward, not the final motion through the air. So then considering that part, in part A, centripetal acceleration, well, your centripetal acceleration's equation, v squared over r. We know v and we know r. We are going to have to convert our centimeters into meters. So then this is going to be 4.2 meters per second, quantity squared, divided by 0.55 meters. That's going to give us a centripetal acceleration of 32.07 meters per second squared. Now, remember this centripetal acceleration. It's not that the ball is speeding up or slowing down by this amount. This is the directional change acceleration. Following that, then the arm continues to linearly accelerate it. So this speed isn't even the speed that it leaves the person's hand with. It's the speed at the end of the circular path. Now in part B, we want the centripetal force. Well, centripetal force is not a new force. It's just a name for a force that's already there that is supplying a centripetal acceleration. So in this case, the arm is applying an inward force to keep the ball from flying tangent as it goes in that circular path. So it's that applied force from the hand that we are actually calculating and then calling a centripetal force. Net force is equal to mass times centripetal acceleration. Our mass was 7.3 kilograms times the centripetal acceleration, 32.07 meters per second squared. Multiply those together, we get 234.13 newtons, and that would be your centripetal force value. Again, the change in the motion that is occurring due to these extra newtons is not a speeding up or slowing down. It is a directional change acceleration. Ponder physics.